Hi everybody, welcome to the third video. It is currently 7 a.m. on Saturday morning, so you may hear a small child cry at any point during this video if my daughter wakes up. So in the last video, we introduced the idea of forcings and feedbacks, and we looked at the ice reflectivity feedback as a way to possibly trigger global glacial periods. In this video, we're going to take a look at the carbon cycle and see how that has affected past climate changes. So in that previous video, we showed 100,000 year cycles of glacial interglacial periods, and we saw that we go into glacials slowly and we tend to come out of them really quickly. And we talked about the idea that northern hemisphere summer insolation can trigger glacial periods, but it can't actually account for the full drop in temperature. This is a really important point. So we can change that insulation, we can melt back some ice or allow ice to grow bigger, but that ice reflectivity feedback is never going to actually account for the full drop in temperature that would be required to have a full glacial period. So we need to look elsewhere for feedbacks in the system that can give us this bigger temperature drop. And today we're going to look at the carbon cycle, in particular atmospheric CO2 and methane, which we know are big greenhouse gases, and we're going to see if those can actually help get us to the observed temperature drop. So the outline is we'll start out looking at ice cores, which give us a record of greenhouse gases and temperature. Then we'll look at the organic and inorganic carbon cycles, and then we'll finish by thinking about how past climate changes might actually inform modern climate change. So ice cores are these amazing records that are drilled from the ice caps, and there's only two of them. There's one in Greenland and there's one in Antarctica. So this is ice that is very thick. It's been accumulating for tens of thousands of years in Greenland, and for easily hundreds of thousands or millions of years in Antarctica. And so this is a big deal to get these cores. You have to set up a very remote camp, fly everything into the camp, and then actually try to drill through the ice. And we'll be looking more at this in lab today. So to date, the most impressive ice core recovered is called the Epica core. It recovered a roughly 650,000 year record. So this is an amazing record, and what makes it special is that it's very high resolution. Much higher resolution than most marine records, but the trade-off is that the time period that it covers is much lower. So marine records go back maybe 70 million years, whereas ice only goes back about 650,000, but at a much higher resolution. And more importantly, ice gives us two records that are tough to get out of marine sediments. One is a direct measure of air temperature from looking at isotopes in water, including hydrogen isotopes. The second thing it gives us is actually a direct measurement of the concentration of atmospheric gas, which is measured directly in bubbles in the ice. So these bubbles in the ice are literally little sampling capsules that lock in samples of gas from the ancient atmosphere and provide us with this amazing record of past greenhouse gases. So let's look at how those greenhouse gases are trapped in the bubbles. Well, it all has to do with how ice forms, and the way ice forms is that snow falls on the ice cap, and then more snow falls on the ice cap. And as that snow piles up, it adds a weight and starts to compress the older snow beneath it. So we go from just actual snow at the surface that's easily exchanging gas with the atmosphere because there's a lot of permeability, to a material called fern, which is kind of a hard-packed snow that's moving towards ice. And as those crystals regrow and they become more hard-packed, it starts to limit gas exchange between the air and the between the air, which is way up here, and the firn, which is way down here. And the connectivity between these pores is starting to disappear. Now eventually, once more snow accumulates, we actually compress everything into ice. And we make that transition into a new crystal structure that's ice, and there's no more gas exchange. We're only left with a few residual bubbles that are locked in that ice. Gas can no longer exchange with the atmosphere, and we now have our sample of atmospheric gas, potentially from hundreds of thousands of years ago, a direct measure of past CO2. Now, how do ice cores record temperature? They do this using hydrogen isotopes as well as oxygen isotopes. But since I've already explained oxygen isotopes in a previous video, we'll focus here on hydrogen isotopes, which are quite important for telling us temperature. And the main process that drives fractionation of hydrogen isotopes is called rainfall fractionation. And in this process, the heavier isotope of deuterium, or 2-hydrogen, tends to condense out of water vapor first, which means it tends to rain out first. So as a cloud starts to come across Antarctica, it starts to cool, okay? And the more it moves inland, the more that cloud cools. It's relatively warm when it comes off the ocean, and it cools as it moves inland across Antarctica. Of course, we know that as water vapor cools, or air masses cool, they hold less water vapor, so it starts to rain. And the first thing we rain out is actually the heavy hydrogen, the 2-hydrogen. And we leave behind more of the light hydrogen, the hydrogen 1. And so as the cloud moves in, this ratio actually gets lower. So the delta value actually gets lower. Now the key point is that if you're standing at any point in Antarctica over hundreds of thousands of years, as the air temperature in general gets colder, that means that more precipitation is squeezed out earlier, and by the time the cloud reaches you in the interior, the ratio is even lower than it would be if the atmosphere had been warmer. So in summary, if you're standing at any point in Antarctica, the ratio of 2 hydrogen to 1 hydrogen will decrease with colder air temperatures, because those colder temperatures cause more precipitation as the clouds move towards the interior. So this is an excellent direct temperature record. And so here's what those data sets look like if you compare them from a single ice core, the Epica core. We've got carbon dioxide in blue, we've got methane in green, and we've got temperature derived from the hydrogen isotopes in red. And what we see is this spectacular correlation between temperature and greenhouse gas. And that is the single biggest contribution that ice cores have made, is this incredible direct correlation between greenhouse gases and temperature. So if anyone asks you whether greenhouse gases are responsible for temperature change, this is a really important piece of evidence over geologic time that they sure are probably the most important driver of atmospheric temperature. And if we model this, we can see that greenhouse gases are definitely the cause of temperature change during ice ages. So the question is, what's actually triggering these greenhouse gases to change as drastically as they are, right? We know that we're not directly forcing greenhouse gases to change over geologic time. All that we're probably forcing is for insulation to change. So we need these greenhouse gases to be changing by way of some feedback within the system. So now we're going to switch gears and look at the organic and inorganic carbon cycles and look at what some of those feedbacks might be that are causing carbon dioxide and methane to change. So we just need to quickly review that greenhouse gases in the atmosphere are part of the carbon cycle, and specifically there's two different carbon cycles we could identify. One is the organic carbon cycle, and that involves basically living things exchanging carbon with the soil and then with the atmosphere. So this would be plants dying, decaying in the soil, and then returning that carbon dioxide to the atmosphere. And we've looked at this in a previous lecture, so that's all you'll hear about it now. The other half that we haven't looked at is called the inorganic carbon cycle. And this involves a transfer of carbon from the atmosphere into the ocean, then into ocean sediment, into rock, and then that rock actually being dissolved or taken down a subduction zone, and carbon being transferred back into the atmosphere. So that's the inorganic cycle. Now note we can break all of these cycles into both reservoirs, which are shown here in red, where carbon can reside, and those numbers are in gigatons of carbon each year. And then the arrows with the blue numbers are showing the fluxes between the reservoirs. So for example, there would be a 60 gigaton per year flux of carbon from living things into the atmosphere. And one key point I need to make here is that you can see that the organic carbon cycle holds way less carbon than the inorganic. So there's not a lot of carbon involved in this, but the fluxes are much higher. So 60 and 120 versus fluxes maybe like 33 or 0.02 gigatons per year. So this is the active but small piece of the carbon cycle, whereas the inorganic is the large but less active piece. But both are important. So I just want to quickly show you the inorganic carbon cycle. And as I just mentioned, this plays out over timescales of millions of years. So a lot of carbon moving, but very slowly. So how does this work? Well, one of the main contributors of CO2 in the inorganic cycle is actually gases that are erupted out of volcanoes. And that gas is derived from melting and dewatering or degassing of the downgoing tectonic plate. So we pull gases off the plate, we erupt them into the atmosphere. Now that atmospheric carbon dioxide then actually reacts with water to make carbonic acid, which can come down and actually weather rocks on the surface. And as those rocks are weathered, that carbonic acid is consumed and fixed and then actually transported into the ocean, where it can then be stored back with sedimentary rocks. In particular, we've already seen that many marine organisms make their shells from calcium plus bicarbonate. So one way that carbon is stored is by actually organisms making their shells and actually dying to become limestone. And then as that limestone goes down the subduction zone again, the CO2 off gases, and we repeat the cycle. So in summary, a couple important sources of greenhouse gas to the atmosphere. We've got the decay of organic material in soils. We've got volcanism, which is part of the inorganic carbon cycle. And then it's also important to note that the atmosphere can directly exchange carbon with the ocean. So that's how we can get greenhouse gases into the atmosphere. How can we get them out? What are some carbon sinks? Well, we know in the organic carbon cycle we can do that by photosynthesis, or the growth of plants. In the inorganic cycle we can do it by chemical weathering of rocks and the burial of sediments in the ocean. And of course, direct exchange with the ocean is also an important part of the of both cycles. So we're now positioned, we know something about the carbon cycle, so we can think about which feedbacks within this system might actually amplify carbon storage. right? We need to get carbon out of the atmosphere and store it somewhere, either in living things or soils, or perhaps store it in the ocean. We got to get it out of the atmosphere if we want to drop temperature during these glacial periods. And we're going to need some feedbacks. So one important feedback is, and this is a positive feedback, is called the ocean temperature solubility feedback. And this is a simple physical law which says that the amount of CO2 or any gas that can be dissolved in water actually increases as temperature drops. So as temperature gets lower, the amount of dissolved gas increases. So what does this mean? This means that as ocean temperature starts to drop, as we head into a glacial period, the ocean is actually then able to hold more CO2 based on this simple physical law. And you can see that this is a big effect. If you drop temperature by even 5 degrees, you're going to get a 10 or 20% increase in solubility. So you could potentially store 10 or 20% more gas in the ocean. So let's look at what happens if we only increase ocean solubility by 5%. How much extra carbon can we store in the ocean? Well, it's a huge amount, especially in the deep ocean, which holds a lot of carbon. We can hold an extra 1,900 gigatons of carbon. So if you look at that, that's more than the atmosphere and living things combined. So if we only increase, if we increase the amount the ocean can hold by 5%, which is totally doable, we could store all the carbon in both the atmosphere and on land in the ocean. So that's a huge effect, and maybe an important effect in storing carbon during glacial periods. So it's worth mentioning that there's obviously a lot of different feedbacks that go on within the carbon cycle, and unfortunately we don't really have time to get into them all. But if you take a class on climate change or read up online, you can learn all about these very complicated feedbacks. In this video, we're going to just finish up with some thoughts or reflections on how past climate change might inform modern climate change. So obviously one of the huge advantages of studying past climate change is that we get to look at a much longer temporal record. We get to look at what's actually happened over hundreds and thousands of years. And that helps us make predictions of what might happen in the future. Also, we've seen Earth at many more extremes than we're at today. We've seen it way hotter, and we've seen it way colder. So studying the past can help us understand, in particular, what happens in these rapid transitions where you go from either cold to very hot, or vice versa, relatively quickly, and start to think about what are the feedbacks that would actually let you make these quick changes in climate. And so I'll just illustrate that with one point here, which is that CO2 over the last roughly 50 years has risen 80 parts per million in the atmosphere. So that's this curve here. In very recent history, the quickest rise we've seen is about 100 ppm over 5,000 years. So not nearly as fast, but potentially comparable. And there are periods in deeper Earth history where we think this rise must have been even faster. So this is direct evidence that what's going on today is much faster CO2 increase than we've seen in recent Earth history. And the other thing this geologic data does is gives us some context in which to think about modern CO2. And here's a couple data points. What we see here is a combination of modern analyzed CO2. So this is CO2 measurements that were actually made by a human being just by capturing the atmosphere. That's in black. And then overlain with these other data points, which are from relatively recent ice core data. And so we can see in the ice core data that CO2 is holding fairly steady over the last 800 years until the Industrial Revolution and then things start to skyrocket. So here we see a nice combination of geologic data with modern data to give us the whole picture of how CO2 is changing as a function of human activity. And then of course we can compare that with temperature measurements that are, in this case, made by humans rather than taken from ice. And we see a great correlation between CO2 and temperature, which is one of the reasons that we are certain that CO2 is contributing to global warming. And the final point I'll make is just that and when we think about modern climate change, people spend a lot of time trying to attribute different aspects of temperature rise. So how much is due to greenhouse gases versus how much might be due to other things. And to do this, we really need to understand the forcings and feedbacks in the system, which are some of the same forcings and feedbacks that have been going on throughout Earth history. So this plot shows the relative intensity of different forcings. So here's the big one, which we know is CO2 and methane, mostly emitted by humans. But there's also some other forcings that are similar to what's gone on in the geologic past. For example, here's changes in surface reflectivity, which nowadays are mostly driven by land use. And then also any changes in solar irradiance, this outside forcing, which has actually increased a bit recently. So there are some parallels between the forcings and feedbacks we think about in modern climate and those we think about for past climates. So there's a summary of what we've talked about. I'll leave you with a concept question and a link to the quiz for this video. And I'll see you next week for our first video on glaciers. Thanks. And my daughter didn't wake up, so that's nice.